Okay, so hello, my name is Roberto Suárez Soto. I work for Alenta. We are a little boutique IT services company, which means we do a little of everything, but mostly we're specialized in content acceleration, monitoring systems too, a bit of security, and also observability. We use different tools, but for observability monitoring, we basically focus on Zabbix. So, model-driven telemetry, where did this happen and how? So, we had a customer that runs the live coverage of TV, radio, and digital content for a big worldwide sports event. We are not really allowed to say the name, but it has a Greek origin, and it's not the World Soccer Euro Cup. So, the scenario was formed mostly by Cisco devices, mostly Catalyst switches, Nexus, and also a few NCS routers. And the customer knew that there was something new available to monitor the systems that wasn't SNMP, which is model-driven telemetry, and wanted to test it and see if it fit its necessities, which was mostly concerned about the usage of internet bandwidth and device availability. We use Zabbix to monitor everything, and we use Grafana to show some information for the visualization because we needed something a bit special. Besides how much it was used on Zabbix 6.0, we monitored about 90 devices. There was, at the end of the event, about 600 gigabytes, and we had an average of 2,000 new values per second with peaks of 3,000. So, what is model-driven telemetry? Model-driven telemetry provides a mechanism to stream monitoring data from the devices that are MDT-enabled to a receiving destination. This is usually different because people, when think about monitoring network devices, is thinking about SNMP, which is getting the data from the monitoring system, from the devices, from the monitoring system. So applications really can subscribe to the data they need. You don't need to poll for a different kind of data. You can just tell the device that you will need this data every time, and it will have it ready for you. It's based on young models, which is a specification that is, it's open. You can see it easily in GitHub. You can see it for every kind of device. You don't have to go to the website of each vendor. You can get it from a single source. And it uses an XPath syntax, which is easy to parse and to use. So the data that you will receive, the monitoring data that you will receive, will also use structured data like JSON and XML. And also the protocol you will use to transfer that monitoring data is not UDP, as in SNMP, but can be raw TCP or even something more advanced like gRPC, which is based on HTTP2. There are really two methods of getting the data, which are dial-out, which is the device will push the data to the monitoring system, and dial-in, which is the more traditional system of going to the device and picking the data you need. In any case, you can use a subscription system where you say exactly what you need. So in each device, you can see here, one example from a Nexus, Cisco Nexus. You define a subscription. Subscriptions is the way that you have to tell the system the data you will need. You have to say what data you need. It may be, for example, CPU data or network interface data. You have to say how often do you need it. When you want the data, you can say you want it every 60 seconds, every minute, every 2 minutes, every 1 hour. You have to tell it where to send the data, where is your monitoring application, and how. And how can be, again, raw TCP, gRPC, or some other options. To configure that, you can use different methods. Usually, netconf is one of them. A protocol system really thought strictly to configure network devices. You can use GNME, which is something similar, but in our case, you use directly SSH, which is the traditional way of using SSH to enter, log into a network device, and input all the configuration. The subscriptions, in this case, are predefined. You define the subscription, you define all the data you need before when you configure the system. But technically, you can use already also subscriptions that you need on the fly. So first, in our case, if you want to push the data from the device to the monitoring system, you add in the configuration all the subscriptions you need, all the sensor groups, which are the collection of data points you will use. You define them with XPath, so you can say exactly what you need. You can use, for example, XPath to say that you need one item or one branch of items, and then you say where you're going to send it. You can have this all predefined, but you can also use it on the fly. So you can dial into the device and say, I want this now. But it's not really the most useful way of doing it. So why should you use model-driven telemetry instead of SNMP? Well, first thing, it uses, or rather, it encourages to use a push model instead of a pull model. This architecturally is easier when you have to design the network policies. Because if you wanted to use a pull model and you have, well, like in this case, let's say 90, 100 devices, you have to go to each of them and define a policy, an ACL, to allow the monitoring system to connect and get the data. In a push system, it's easier because you only have to define a network policy to allow all the devices to push the data to a certain, in this case, a certain TCP port in the monitoring system. So it's easier on the, on the administrators, and the configuration is simpler. Also, you don't have to, it's easier on the system, on the monitoring system, because you don't have to poll. So in this case, the device will push the data as soon as it's ready, and you don't have to go there and pick it up. So it also uses TCP and HTTP 2 transports, which are stronger and more useful than plain UDP. Because, for example, TCP means that the connection will be more stable, and, for example, if it fails, you won't have the same error. If you have used SNMP, you will know that when there is a timeout, you never really know if it's because the packet was dropped in the line, or you just use the wrong community, or there is something else, because you don't have really error checking. That's not that doesn't happen with TCP, because it's focused on sessions and connections. And you also have other transports based on HTTP2, which have encryption and compression. Also, you will receive the data on JSON and XL. You can choose which of them, which are easier to parse and also allow for more complex data structures. And in the end, again, CPU and memory use in the monitoring application will be lower, because you don't have to really poll each of the devices, poll them every time you need a new data, because the device will be who will send the data to you and will do it at predefined intervals. So you just have to be waiting for it. So how did we use, or how did we really put all this model-driven telemetry into Zabbix? So Zabbix by default doesn't support this. So we thought, okay, how do we get all this data from the devices to Zabbix, and then, even if you have this data in Zabbix, how do we parse it and turn it into entities that Zabbix will understand? So first, to receive the data from the devices, we use Telegraph, which has a model-driven telemetry plugin made by Cisco itself. So with this, we got all the data sent to Telegraph, and then that parsed the data with the Cisco plugin, but then we'll still have to put all that data into Zabbix. And for that, we reached that gap using a custom plugin that we made ourselves. So the whole architecture was we defined die-allowed subscriptions on the devices, so they knew that, I don't know, every 10 seconds, every 2 seconds, we wanted this data or this other data sent by gRPC to this port in this IP. We, in fact, had to configure them using scripts because there were too many devices to do it by hand. So from them, we wanted two kinds of statistics. One of the promises of model-driven telemetry is real-time monitoring. In this case, after a few studies, we went for two different types of what we call real-time, which is not really real-time. So we said we have hard real-time, which is really statistics taking every 2 seconds, and soft real-time, which will be statistics taking every 10 seconds. We use then model-driven telemetry to send this to Telegraph using RPC. Telegraph feeds this data to the Cisco plugin, and then that was fed to our custom plugin that acts at the same time as a sort of server and client to Zabbix. At first, the prototype was in Python, but there was too many data and there were too many devices, so in the end we had to re-implement it in Golang. So how did this connector work? This connector did two things. As I said, it was both a server and a client for Zabbix. It was a server because Zabbix could query it for discovery data. So we had a discovery rule shown in this place that every, I don't remember exactly the time, but every few seconds or every 3 minutes, query the connector for new data, for new data points that were defined or that had come from a device. It could be, for example, that it finds all the network devices, all the kind of CPUs or memories that the device has. And then once we have that discovery rule and we have item prototypes that create all the items that that device can provide, then the same connector feeds all that data that comes through model-driven telemetry to Zabbix. So both were needed because we didn't really have a way to know what items, what data points were defined in the devices without the discovery. Then for that, we defined two templates, and we use all the same templates in each model. So we had two, one for a catalyst, and then one for Nexus, and now another one for the router. So, well, it's not really, yeah, it's better here than my monitor. You can say these were all the prototypes, item prototypes that we created based on model-driven telemetry. As you see, there are only 2 master items using Zabbix Trapper, which was the data sent by the connector that we made, and then everything else is dependent item. This, after all, it was data that came in JSON form, and we could parse it quite easily into something more coherent for Zabbix. So this is one problem that we found and that we really didn't expect at first. Why having soft and hard real time? And then when you use 2 seconds data points, what happens with the graphs? As you can see, this is 2 hours, and if we use only 2 second data points, it was, well, quite messy. This is only 2 hours, and you can see a lot of points. So the connector also provided a copy of that data that was instead sent every minute. So we could have a lot of detail for small intervals, but when we open that window, we could have something more easy to see for humans. It's meant in a graph that covered a few hours. So what we learned with this? So first, model reliability works as advertised. It's not that we really didn't expect that, but it's something that we had to try and we have to confirm. So we really were able to gather data in almost real-time fashion. We sent at first 2 seconds. I think we ended up using 5 seconds. It was helpful for a lot of issues because we could really see what's happening. For example, if some switch failed or if some port was down, we could see it really quickly, which was needed in this case. And so we found some things that we didn't expect. Once we knew what they were, there wasn't anything else that we have done that we needed. So it needed a different point of view when debugging problems because usually control who sends data and when. And then, so at first we thought that once defined, we could also know exactly when the data was going to be sent. In the end, it didn't really happen that way. So there were some rough edges. Real time is not really so much real time when you are really go down to it, because we found that some devices couldn't really provide the data as fast as we needed. So at first, again, we wanted the data every 2 seconds, but we found that some devices couldn't handle it when we asked for too many data points. So CPU usage was quite high anyway, not really what we expected. And also we found that some interface counters, for example, some network interface counters weren't updated in real time. So you could ask for them every 2 seconds, every 3 seconds, every 5 seconds, but if they were generated every 10 seconds, it wasn't really useful. So something else that we found was that you have young models which should be used every time, there were small differences. For example, once you could receive all the data points in one big JSON structure, and some other times you could receive a few JSON responses with one of the data points. In the end, this is not really a problem when you know it, but it's not at first. We didn't know about it, and we had to change our templates and even change the code of the connector to be able to parse it properly. So we also needed some workarounds due to the lot of data that we put in the database. Using 2 seconds at first, we found that some DB queries were noticeably slower. We didn't really know why, but we thought it was because the density of data points in Zabbix was very high. And also, as we use Grafana dashboards, we found that the Zabbix plugin for Grafana wasn't performant enough for some repeats. For example, when you use, I don't know, if you want to know the state for 40 network interfaces, and you want to know it every 2 seconds, sometimes the queries took more than 2 seconds, so you didn't really have the results fast enough. In the end, we use SQL queries for these dashboards because that was the only way to have the data fast enough. But that made dashboards very complex because we couldn't use really a lot of the features that Grafana allows for having, for example, to not define each of the network interfaces, each of the bandwidth meters, or each of the memory or CPU counters. So it worked, but you had to love it because it needed some love. And that's all. So questions?